Okay, this is section 8.6, Lewis structures and formal charge. We're going to do a calculation now, which is useful for determining the quality of our proposed Lewis structures. Okay, we've learned so far that the underlying principle behind Lewis structures is the octet rule, right? So, for example, oxygen becomes stable when it shares a pair of electrons with each of two hydrogen atoms, thereby giving it 8 total valence electrons. 2 in the form of lone pairs, 4 in the form of lone pairs, because each lone pair is 2 electrons, plus 2 bonds, and each bond has 2 electrons. So that's the octet rule. It turns out that it is not the case that all stable structures possess octets, as we'll see as we move along through the chapter. So for that reason, we need another method of evaluating the quality of a Lewis structure. So we may realize that, this structure right here is problematic because the carbon atom only has 4 electrons, and that's no good. So that Lewis structure is no good. That's using the octet rule. But now we're going to use another method, which is called the formal charge, which is a calculation we do. Okay? Much in the same way that we calculate the octet, how many electrons are around the atom, we calculate the formal charge. So let me show you the equation you'll use. There aren't really symbols for this, so we just sort of write it out in words. The formal charge is equal to the number of valence electrons minus the number of associated electrons. And so the trick here is to figure out what we mean by associated electrons. Okay? So formal charge is calculated for each atom. In a Lewis structure. And so they're represented in a particular way. So let me show you a Lewis structure. This is the nitrate ion. There we go. You'll be able to identify, remember we use brackets to indicate that it's an ion. You'll be able to identify the formal charge calculations. Sometimes what that is done is the formal charge is indicated in a circle near the symbol for the atom in the Lewis structure. So for example, the nitrogen here has a formal charge of +1, and we put plus or we put minus. Formal charge can be positive or it can be negative. If it's plus, we put a plus sign. Here it's -1. Here it's -1. And here it's 0. So the formal charges are calculated for each atom and can be represented in the Lewis structure itself. In this case, we've indicated that the formal charge of the oxygen atom can be either -1, for 2 of the atoms it's -1, or it could be 0, for 1 of the atoms it's 0, or it could be positive. In this case, nitrogen is positive. Now I want to make a comment about positive or negative or 0. If you have a formal charge that's not 0, meaning it's +1 or +2 or -1 or -2, you generally will not see formal charges greater than +2 or less than -2. That would be very strange to see that in a proper Lewis structure. But if they're positive or negative, the best Lewis structures arise when the more electronegative atom has the negative formal charge. In fact, I'll put that in a circle, the negative formal charge. The less electronegative atom has a positive formal charge. So if there are formal charges that are positive or negative, the more electronegative element should have a negative formal charge. And if there's a positive, the less electronegative atom should have a positive formal charge. So if you look up electronegativity values, for oxygen it's 3.5, and for nitrogen it's 3.0. That's the Pauling electronegativity table. Oxygen is more electronegative. Notice it has the negative formal charge. In this structure, nitrogen is the less electronegative atom. It has the positive formal charge. And that's generally, not 100%, but generally that's what's observed. Okay? So now what I want to do is I want to run through the calculations for a couple of structures using this equation. Okay, so let's take ozone as an example. Ozone is O3. Now it turns out it's very rare for molecules with only 3 atoms to form rings. They generally form straight chains. So we wouldn't typically see this. There are some molecules that form rings, but if there's only 3 atoms, they're relatively rare. They're unstable for various reasons. So ozone is actually just, in terms of a Lewis structure, just a straight line. Okay? Now let's just go ahead and draw a reasonable Lewis structure. Oxygen is in group 6A, so it has 6 valence electrons. There are 3 oxygen atoms, so that's 18 valence electrons. We've already used 4 valence electrons, so we're down to 12. So as we learned in the previous section, what you do is you fill out, that's a 14. You fill out an octet for the surrounding atoms first. This is a strategy. So now the 2 surrounding oxygens have 8, right? Because they have 3 lone pairs and a bond. But that takes care of 12, so we got 2 remaining. So I'm going to put the 2 over here. So now the surrounding atoms have 8. The oxygen in the center, the bridging oxygen, has 6. So what we learned in the previous section was take one of the oxygen atoms that has 8, push a pair. We indicate a change in the Lewis structure by using a double arrow. And now we have a double bond, right? This pair right here formed a double bond. Now the oxygen in the center has 8. Let me clean this up a little bit. Make it a little nicer looking. There we go. Each oxygen now has 8 electrons, okay? Now you may have noticed, well, wait a minute, I could have pushed the pair from the oxygen on the right. That's absolutely right, and that's actually a different topic that we'll discuss later. But for now, each oxygen has 8. So what I'm going to do is I'm going to run us through a calculation of the formal charge for each oxygen atom. It's valence electrons minus associated electrons. So we do it for each oxygen. So let me just draw a little dashed arrow out here to show that I'm going to do this particular atom over here. So the formal charge for that oxygen would be the number of valence electrons. That's 6. You already know that number. It's in group 6A, so it's 6. The trick here is how do you calculate associated electrons? The way it's done is you look at the atom structure, in the structure. A lone pair counts as 2. 2 electrons. And a bond counts as 1. because we're assuming that the bond is shared equally by the two atoms in the bond, associated with the bond. So we split the difference. A bond has 2 electrons, each atom gets 1, okay? So a bond is an electron, a lone pair is 2. A double bond is 2, right? Because one bond is 1 electron, 2 bonds would be 2 electrons. So let's do it for this oxygen. We're going to subtract 1, 2, 3, 4. So there's your 4. A lone pair is 2. There's 2 lone pairs. There's 2 bonds. 6 minus 6. Why did I just draw that negative there? That's 0. So the formal charge of that oxygen is 0. In general, the closer formal charges are to 0, the better. Okay? So it's usually a good sign in a Lewis structure, evaluating it if you get zeros. You won't always get zeros, but if you do, that's a good sign. Now let's do this oxygen here. Again, it's oxygen, so 6 valence electrons. Now, there's only 1 lone pair, so that's 2. And there's a total of 1, 2, 3 bonds to that atom. So that's 3. This is 6 minus 5 plus 1. So the formal charge is plus 1. Last oxygen out here. Formal charge, 6 minus. Now there's 3 lone pairs, so that's 6 right there, and 1 bond. So this is 6 minus 7, which is minus 1. And again, we indicate the negative 1. I'll do it right here, because there's already a little dash there, as a circle next to it. What we just did there was we calculated the formal charge of each atom in that structure, okay? In general, oops, sorry about that. In general, zeros are best. So for example, if I have some kind, I'm just going to make up a structure, and this is 0, and this is 0, and this is 0, that is better than, it's greater structure than, let's say, I don't know. Oops, sorry, AAB. Let me just be clear about this. We're not changing the arrangement of the atoms, we're just changing the Lewis structure. Plus 1, plus 1, 0. Okay? This would be better than that. So it is possible to have formal charges of plus 1 or minus 1. We just saw that right there. But in general, we draw Lewis structures to give us formal charges that are closest to 0. Okay? Plus 1 and minus 1 would be better than plus 2 and minus 2. Right? Another thing to say about them is that if you have an ion, the sum of all the formal charges in the molecule, or the ion, should be equal to the charge of the ion. Okay? So let me show you again a Lewis structure for the nitrate ion. If you look at the formal charges of all the atoms in here, the nitrogen is plus 1. The oxygen here is 0. The oxygen here is minus 1. And the oxygen here is minus 1. If you add up minus 1, plus 1, and 0, you get minus 1. So the sum of the formal charges will actually work out to be equal to the charge of the ion. Okay? Now, we can use the Lewis structure, we can use the formal charge calculation to determine whether the structure that we've drawn is a reasonable one. Okay? So coming back to the ozone molecule, O3, if you add up the charges, you get 0, because 0 plus 1 and minus 1 add up to 0, so that's reasonable. Okay. And plus 1 and minus 1, although they're not 0, they're pretty close to 0, so that also seems reasonable. Okay. So practice doing the calculations. Again, you do it for each atom, and then you can use that in your evaluations.